good afternoon. Thanks for being here. So today's seminar speaker is Alex Schenkman. Alex is originally from the Boston area, but did all of his education at the University of Oklahoma, where he got his PhD. We actually graduated together in 2012. After that, Alex worked as a postdoc at the Center for Analysis and Predictions for Storms, CAPS, which is an entity within the University of Oklahoma. Soon after that, Alex was about to be a research scientist at CAPS before took a plunge and went back home and now works as a scientist at Berkshire Hathaway. So a little bit different career route than most of the speakers that we have. I did not invite Alex here today to talk about Warren Buffett. That will not be what he's talking about. But the reason that I'm excited he's here and to give this talk today is because, in my opinion anyway, Alex wrote probably the most important severe weather paper, certainly of this decade, which he's going to talk about today. I won't steal your thunder, but one of the most important issues in tornado science is trying to figure out where rotation comes from very close to the ground. And Alex discovered something that had been kind of long lost and forgotten in regards to that. And so he's going to talk about that today in his talk, examining tornadogenesis using a high-resolution simulation. So let's welcome Alex.
All right, thank you. I'm glad we're getting this in before the end of the decade, just barely. But yeah, thanks for the introduction, and thanks for having me here to kind of relive the glory days of studying high-resolution simulations of tornadoes. And this is work that I started towards the end of my PhD and then continued as a postdoc, and was working on another case before taking the plunge into a private company and insurance world. So I just want to start off, just to get everybody on the same page, a little bit about supercells and supercell rotation. So supercell thunderstorms are different from normal everyday thunderstorms in that they rotate. They last for hours and hours. There's examples of supercells tracking for hundreds and hundreds of miles. And they occur given kind of a favorable combination of wind shear and instability. They're responsible for the vast majority of strong tornadoes and large hail. I think large hail is sometimes overlooked from supercell thunderstorms, but almost all of them have gigantic hail. And you can have supercells anywhere in the world, or in the mid-latitudes at least. But by far the U.S. plains is the most likely place that you're going to see a supercell thunderstorm. So we have this conceptual model from the late 70s from Lemon and Doswell. It's kind of been adapted, but it's kind of stood the test of time for supercells. You have this main forward flank downdraft, a lot of precipitation, heavy rain, small hail that falls away from the updraft area. Let me see if I can. Yeah, so a lot of heavy rain in this area, small hail, it's cold. Closer to the updraft, you have large hail that falls on the north side of the updraft. Kind of tucked into the updraft and rear flank area here is where you'd most likely see a tornado. You have these boundaries, forward flank gust front, which has been found to be a little bit subtle over time. I think initially some of the modeling studies showed really pronounced forward flank gust fronts, but in general these are more of convergence boundaries and slight wind shifts across this area. And then you'll have this strong rear flank downdraft with a strong rear flank gust front, so a very pronounced change in wind direction along here. This is just generally the way in which conceptually we think about supercell thunderstorms. So as I mentioned before, supercells are unique in that the updraft rotates. It's very well understood how the updraft gets its rotation, so that when the thunderstorm updraft begins, it tilts and rearranges environmental wind shear or horizontal vorticity, and you develop a mid-level rotation, a mid-level mesocyclone. Over time, that mid-level mesocyclone intensifies, and pressure forces and nonlinear accelerations help the storm persist and help the mesocyclone strengthen. So this is pretty well understood. No real issues here in terms of how the mid-level rotation happens. More uncertain is the origin of low-level rotation. So it's kind of, once you get the mid-level rotation, sometimes in some situations you'll start to see low-level rotation develop, a low-level mesocyclone, and then maybe a tornado. And the origin of that rotation is kind of what comes into question. There's this general theory that because the air parcels are ascending into the updraft, you can't have significant vertical vorticity until the parcels get far above the ground, because by the time the vorticity tilts upward, it's moved away from the ground, so that doesn't explain low-level rotation. So generally it's accepted that you need to have a downdraft to get near-surface rotation to develop. Recently, and if I was still actively doing research in this area, I think I read this paper and was pretty excited about it. So Rotuno et al. Recently showed that you actually don't need to have vertical vorticity right as the parcel reaches the surface. What's more important is that if parcels are accelerating and horizontal streamwise vorticity is accelerating into an updraft, it can rapidly turn vorticity upward. So you don't necessarily need to have vertical vorticity as the parcel is descending. But at the time I was doing this work, you did. So we'll go on that assumption from here on out. But yeah, it's an interesting result. There's a lot of implications in terms of what I'll show later that you could kind of take away. So there's a mechanism where storm-generated cold outflow has been used. Storm-generated cold outflow generates horizontal vorticity, and that vorticity gets rearranged in a downdraft to explain the origin of low-level rotation in supercells. So this is kind of known as the baroclinic mechanism. This is a cartoon of how this works. So you have a air parcel that's planar descending along a gradient in descending along a gradient in temperature here. So this is a planar view, and this is a cross section for this air parcel. Parcel moves along. The red is the horizontal or the vorticity vector. Parcel moves along, so as there's vorticities being generated pointing south in this situation along the trajectory of the parcel. It's streamwise vorticities being generated. As the parcel descends, there's continued horizontal streamwise vorticity because it's still in this temperature gradient. And that allows the vorticity vector to slip from the velocity vector so that by the time the parcel gets near the ground, it already has this kind of angle and vertical component to it. So this has been the kind of generally accepted way in which rotation originates in tornadoes, is that these parcels track along the gradient in temperature. As they descend, you get vortex line, they call it vortex line slippage from the velocity, from the streamlines. And then the vorticity gets stretched extremely since you already have vertical vorticity here, it goes into this updraft and you get strong stretching and it spins up into a tornado. So that's all well and good. There were simulations in the 80s that basically confirmed that. And then there were some field projects that went out and actually looked at the thermodynamic characteristics of tornadic supercells. And this is where it gets a little bit strange. The observational data found that cold outflow tends to be associated with non-tornadic supercells, and that strong tornadoes are associated with warmer cold pools. In fact, in this paper, this figure's from Markowski's textbook, but in his paper, the strongest tornadoes barely had any cold signature at all. So there's this contradiction, or this kind of, you have to explain why you need this cold air to have rotation, but then why is it that the warmest supercells are the ones that are producing the strongest tornadoes and the most prolific tornadoes? So a Goldilocks explanation was proposed to deal with this. Basically, you need cold air. It can't be too cold, because otherwise the storm becomes outflow dominant and sweeps away the developing rotation. But you need just the right amount of cold air to develop rotation in a tornado with a supercell. So that's plausible, but it's kind of a strange. Seems a little random, maybe. The other thing I'll talk about a little bit more later is in that conceptual model. There's this kind of idea of like a static storm where you have this rear flank downdraft and forward flank gust front. When you actually start to look at supercells with higher resolution, you start seeing there's a lot of unsteadiness in the storms. And one thing that's been as modeling has evolved and become higher resolution, and as observational studies have been able to look into the kind of rear flank area of supercells, these internal momentum surges have been found to be basically ubiquitous in supercells. So there's not a constant RFD that's just moving along. There's these surges of momentum that come in behind the main gust front over and over and over again with a very short period. They're very variable in terms of their thermodynamic characteristics. So you can have cold surges in a storm. The same storm can have warm surges, cold surges, all mixing up together. Some of the work from Finley and Lee, they found that the warmer surges are generally associated with tornado intensification or tornadogenesis, and the colder surges, dissipation. So these are interesting. There's not a good explanation as to how these originate, and I'll show some analysis that I did to look at how they originate in the simulation that I'll go through. So just some motivation for doing this. It's very, very difficult to collect observations of supercells. It's expensive to go out in the field with radars and people, and then there aren't a lot of them. It's very hard to forecast how to get in position to observe the storms. But in comparison, computational time is cheap. You have all the variables you need in the model. You just have to have the time to analyze it. And you can model the storms after they occur, so you don't have to set up and figure out where you need to be. So the kind of approach here is to use a high-resolution simulation of a real event to study just some of the things I described. But the big assumption here is that if you start a model based on the observations that you assimilate into the model, and then the free forecast that you let run evolves in a similar manner to the actual event, then you assume that the dynamics in the model are the same as in the atmosphere. So that's the big assumption. If that's not true, everything I'm about to tell you is a lie. If just by coincidence this highly nonlinear storm evolved in a way that replicated the atmosphere, and it was just completely coincidental, then I'll retract the paper next decade. But here's an example of this. So this is the case we're going to look at. This is the observed radar from this May 8th, 2003 supercell, which actually this is like one of my first storm chases when I moved to Oklahoma. I didn't know what I was doing, and our car, I think, ran out of gas. So we didn't see we saw the tornado very briefly, but then we never caught back up to it. And then this is the forecast from a high-resolution. This thing is just not. This is the forecast from a high-resolution simulation. This is the one that we analyzed. So these, in general, there's pretty good agreement here. There's some problems up here. It's probably a microphysics thing. But then, in general, you have the forward flank downdraft. You have the rear flank. The positioning is pretty good. The timing is really good. And so we can look at this and see, okay, is there a tornado in this simulation, and how did that tornado form? Same thing here. This is from a different case I worked on. This is like a 3-hour forecast of this mesoscale convective vortex, and I mean the correspondence is really good here. So you can, in this case, there was a non-supercell tornado, and we looked at the origin of that and had some confidence that maybe the dynamics were the same. So we move on to the 8 May 2003 supercell, which I'll talk about pretty much for the rest of this talk. It was part of a very large, very prolific convective storm, multi-day outbreak in the plains. I think 5 out of 6 days in a row there were large tornado outbreaks somewhere in the plains. So much so, I mean, there's a paper about this, because it just, every single day there would be a big tornado outbreak in this week. And actually, since this was my first spring in Oklahoma, I just assumed it was like always like that. It wasn't. The drought years came later. But so this supercell formed, I think, early afternoon, west of the Oklahoma City metropolitan area. Very, very quickly developed a strong tornado that went through Moore, Oklahoma. It's the second time they had been hit in 5 years by a high-end tornado, and did quite a bit of damage. So briefly, I won't go through this in depth because there's a lot of detail as to how we do this experiment. But basically, this is multiple nested simulations on the lowest resolution grid, the 9-kilometer grid, which takes up a much bigger area of this, but just for display purposes. So this is 1/16 of our lowest resolution grid. I think we assimilate just conventional. Try to remember now. No, we assimilated radar data and conventional observations on that grid, and then using 1-hour cycles. So this is trying to spin up the background forecast, basically get at the environment right, so that later when you go in and we do these 5-minute cycles, where every 5 minutes we assimilate the next radar volume, the environment hopefully is correctly analyzed, the large-scale environment is correctly analyzed, so that the model is not just going to reject the radar data. We used ARP's 3D VAR, so a 3D VAR system to analyze the winds from radar and from conventional observations, and then a cloud analysis to assimilate the reflectivity. Cloud analysis is a good way of thinking about the cloud analysis is it's like a smart thermal bubble. You take reflectivity observed above a certain threshold, and you add energy to the model in those areas. And then the model takes that in and turns that into a convective storm that lasts, given that you have the environment correct. So then within that 1-kilometer domain, there's a 100-meter grid spacing nest, and then within that 100, there's a 50-meter grid. These simulations get huge, so you have to really nest down to the area that you're interested in. The 50-meter grid is still big enough that it contains pretty much the entire supercell, though. And so here's the 1-kilometer forecast. You can see pretty good correspondence just in terms of storm evolution. This thing's totally shot. Just in terms of storm evolution, pretty good agreement. And so I think originally, you run one of these, and if it looks good, it's a candidate to kind of zoom down and run this nest on. Sorry, this is radar reflectivity. Simulated, it's observed and simulated radar reflectivity. Yeah.
Also, what is the size of this storm again?
What's the size? This is Oklahoma County, so I think this area shown is probably like, I think this is like 40 by 20 kilometers each plot, so it's probably a 30 kilometer, 30, 40 kilometers across. And so we run the 50-meter grid spacing simulation, and we get remarkable correspondence between the forecast and the simulation. I think at this point, this would be a 31-minute forecast, starting from, I think 2140 UTC is when we stopped data assimilation. So this is pretty good. This is about as good as it gets in these high-resolution simulations. So then we looked at the maximum wind field produced by the storm, and you see that this is the observed tornado track from the event, and this is the forecasted tornado track from the event. So there's an offset here. The actual event is stronger, longer lived, but in general, I mean, these forecasts don't happen that often. a 31-minute forecast of a tornado start time that's almost perfect is pretty amazing. I mean, if you lived here and I told you to get out of the way and you drove here, you'd be upset with this forecast. But in general, this is pretty good. And so based on this, we're going to look at how these two tornadoes form in the model to try to get an idea of what's going on, maybe in the real atmosphere. So this is just an overview of the first tornado. These are vorticity contours, vertical vorticity contours. So the tornado starts as kind of this single cell thing. It's really pretty messy. It goes through a weakening stretch briefly. It re-strengthens, forms this ring structure, two-cell kind of vortex structure, and then eventually weakens. So the tornado goes for about 15 minutes. There's a million things you could do to try to figure out why this is going on, but we're more concerned with how this happened to start. So I'm going to look at how does this tornado form in the very beginning in the model, because the longer the forecast goes, the more complicated it gets to analyze what's going on, because things just get more and more crazy. All right, so how does the first tornado form? So early on, before the tornado forms, after looking at basically just manually looking at these loops forever, I picked out there's basically 3 areas of vorticity that play an important role in the tornado formation. And so I'm going to call those V1, V2, and V3. V1 forms kind of at I drew in a gust front here. This would be like a forward flank convergence gust front. This is kind of a rear flank gust front. We're zoomed way, way in now. So this is 4 kilometers, 4 by 4 kilometer this image. So V1 is sitting here kind of on the edge of this gust front. V2, the pink shading is vorticity again, is starting to show up just to the north of V1. A little while later, V2 is just kind of sitting there. V1 is pivoting around V2. And then this internal momentum surge, which I've marked with this dashed line, is starting to show up to the northwest. That's 40 seconds. So another 40 seconds later, V1 and V2 have merged into something I'm calling a pre-tornadic vortex, a PTV. PTV is just kind of sitting there and swirling. I call it a PTV because the wind speeds aren't that strong with it. It's already a well-defined vortex, but it's a very low-level feature, and the wind speeds are pretty weak at this point.
What level is this?
This is 20 meters above the ground. That's lowest model grid near surface. So at that point, this rear inflow is on its way. It's coming towards the PTV. And then this area that I'll call V3 emerges on the left side of the internal surge. Kind of pivots around. PTV is still kind of sitting there. And then everything collapses in, and voila, Tornado 1 is born. So that I think that entire sequence is about 2.5 minutes when these things happen. So the storms are, I think one thing that I kind of took away from doing this is like, storms are very non-steady. This isn't a half of a 88D radar scan this would have happened. So in 2.5 minutes, all this is going on. So it'd be really hard to observe this. It'd be very, very, very frequent radar updates. Thermodynamically, it'd be really difficult. So in order to look at how the tornado comes about from a vorticity perspective, did a lot of backwards trajectory calculations, had 2-second model output for those calculations, which these things took a long time. There's this issue where if the trajectory height gets below the lowest model grid level, you have to figure out how to force it. It's less of an issue for a simulation that includes a surface drag parameterization, because if you have a free slip condition, your vorticity goes to 0 below the lowest grid point. But that's dealt with better, and it's easier to do this in where you have a drag parameterization turned on. So we just use the forcings at the lowest scalar point when they go below that point. One caveat here is that the trajectory length is limited by the fact that the tornado forms like 11 minutes into the 50-meter simulation. So you can't go way, way back and rule out. You can't say anything about what happened more than 11 minutes before this. So we're going to look at a characteristic trajectory that goes into each vorticity maxima. So first, V1. V1, a characteristic trajectory that would go into V1 comes out of the kind of the downdraft area, tracks very close to the ground. The red arrows are vorticity, horizontal vorticity. So it tracks very close to the ground. The shading here, I think, is W. And then the dots are height above ground of the trajectory. So it comes in, rises briefly, turns, and then descends, and then goes into V1 near the ground. So we look at the vorticity tendency equations along these trajectories. One thing that we did a little bit differently that I hadn't seen was when we looked at tilting of horizontal vorticity into the vertical, we broke down whether it was tilting of streamwise or tilting of crosswise vorticity. Usually in the past, those things had been combined, but I think it helped figure out what was going on. So we have all these terms here. We have, frictional term, baroclinic term. Tilting and stretching is kind of buried in a term. When you look at things in natural coordinates, you have this exchange term, which is not if you look at Cartesian coordinates, that doesn't show up. But that's basically just the rotation of the coordinate system. Streamwise has a different meaning as the parcel moves, and so that's crosswise or streamwise to crosswise or crosswise to streamwise are going to get exchanged as the coordinate system rotates. Okay, so these are integrated. Those equations integrated along the trajectory starting from the initial value. The light blue line is the integrated total, and the dark blue line is the actual total in the model at that point. The closer these lines are together, the better, because that means that you're not missing something. It's very, very hard to do these trajectory analyses. There's a lot of potential sources of error, especially in strongly convergent flow. So if you think about something converging in backwards time, that's divergence. So any little error gets amplified in backwards time. So any tiny round off error, any small error in positioning or from the fourth order interpolation can kind of get crazy. That's why it's really hard. I said earlier you could look at the tornado and try to figure out how all the tornado dynamics are going on. At that point, the flow is so fast that your errors if 2 seconds is not enough, it's not frequent enough to assume steady state when you do these backwards trajectories. You can't assume a linear transition from one time to the next when you start looking at really fast flows. So it's easier to do it when the flow is still kind of slow in the developing phase. Okay, so all that said, the streamwise vorticity for the parcel is here in this panel, and in this panel it's crosswise. So you see that the crosswise vorticity budget is dominated by frictional generation as the parcel is moving along the ground in the beginning of the path, and then as it gets near the ground again later in the path. Importantly, there's this exchange that goes on as the parcel takes this bend. Maybe I'll try to use the pointer on here because this laser pointer is just, let's see, it's gone. Whatever. I'll just point. Here we go. So you have these two periods where there's exchange from the crosswise to the streamwise as the parcel is bending here, and as it's descending into V1. Importantly, the baroclinic term is the solenoidal term, and the baroclinic term is almost zero. So there's not a lot of baroclinic vorticity generation going on, unlike a theory that would explain the earlier theory that I showed that would explain rotation of the ground. When you look at the vertical budget, you can see this is the parcel height. So you see the parcel rises, parcel descends. As the parcel is descending, there's positive tilting of the streamwise vorticity into the vertical. If you remember, that streamwise vorticity was exchanged from the crosswise vorticity. So you had the generation of frictional vorticity in the crosswise direction. It's getting exchanged into the streamwise direction and then getting tilted into the vertical. So basically, frictional vorticity is the origin of rotation, low-level rotation. The origin of that horizontal vorticity that gets turned into the vertical is friction, not baroclinicity. This is similar to the schematic I showed a minute ago. This is a plot just of the inclination. So this is the slippage between the vorticity and the velocity fields. So you can see the vorticity has a positive inclination compared to the velocity field as it's descending here. So as this frictional vorticity is being exchanged into the crosswise as the crosswise is being exchanged into the streamwise during descent, you're getting this angle to develop, which is similar to that Davies-Jones and Brooks thing I showed earlier, except it's not a baroclinic process. It's friction that's causing the vorticity. So again, this is the schematic I showed earlier where the parcel comes along. The horizontal vorticity generation causes the slippage between the velocity and the vorticity vectors, and you get a lot of vertical vorticity in the ground. So I'll call this a modified Davies-Jones and Brooks mechanism, which is going on for this parcel. So in this case, the parcel's coming along very close to the ground in the cold pool. There's large crosswise vorticity generation going on from friction. As the parcel turns, it gets exchanged into the streamwise direction. So this exchange term is acting like the baroclinic generation term, and it's helping to pull the vorticity vector off of the velocity vector in this case. And so then during descent, you have this angle between the two fields, and it proceeds as the standard mechanism, the baroclinic mechanism. Okay, so what about V2? V2 is different. All the parcels for V2 kind of drag along the ground. You get enormous crosswise vorticity, and then they kind of come in on the edge of this low-level updraft that's along the rear flank gust front. So looking at the budgets, the vorticity budgets for those, you see that there's very large frictional generation as the parcel comes along the ground. The streamwise actually diminishes because of convergence. It's negative stretching, so as the parcel slows down here, the streamwise vorticity is getting diminished. And when we actually look at the vertical budget, you see that the tilting that's responsible for the positive vertical vorticity is tilting of crosswise vorticity into an updraft without a downdraft. So this is when I said earlier that Rotuno paper excited me. This is why this was very difficult to justify and review how we were getting vorticity right near the ground without a downdraft. Our reviewers did not like this because they said that's impossible. You have to have vertical vorticity at the ground for there to be vertical vorticity at the ground. You have to have a downdraft. It has to form in a downdraft. But in this case, this is just a parcel that's being tilted. There's very extreme tilting of vorticity right near the ground because there's a strong updraft just above the ground. For V3, which is the trajectory that goes through the internal surge, it's kind of a combination of the first two. V2, I would say, is kind of analogous to the beginning of mid-level rotation in a supercell. And V1 is analogous to the Davies-Jones and Brooks downdraft model. This one kind of does both. So the parcel comes from pretty high up in the internal surge, rapidly descends, and then kind of comes along the ground, and then at the very last minute, it does turn a little bit here along the leading edge of the gust front. So looking at the budgets for those, kind of shows exactly that. There's streamwise vorticity is being generated by exchange at the very end here, and there's frictional generation of vorticity as the parcel gets near the ground here. And both of those, it turns out, contribute to the vertical vorticity. You have tilting of both streamwise and crosswise vorticity. So I think that you're getting, in essence, the V2 effect where the gradient in updraft is tilting the crosswise vorticity, and also that Davies-Jones and Brooks type of effect where during descent, the turning of the parcel is acting to pull the vorticity vector off of the velocity vector. Tornado 2, really quickly. I thought about not even talking about this because it's kind of it's a much simpler process. But it is kind of interesting in light of some of the descending reflectivity core stuff that people have showed. So Tornado 2 forms as a weak vortex kind of in the inflow area of the storm. So Tornado 1 is ongoing at this point, and out maybe 10 kilometers east, this weak area of vorticity forms. and it strengthens, and it just kind of goes through. It becomes a strong vortex and then dissipates. And as this V4 at this point encounters the rear flank gust front, that's when you get tornadogenesis. And so same budgets for this parcel. We have a lot longer time now because we're 20 minutes into the simulation by the time V4 forms. And the reconciliation in the budgets here is really good. That light blue line is like directly on top of the dark blue line. So in this case, there's this environmental crosswise vorticity, which we have to call environmental because, again, the parcels don't go back before. But this is likely, given the height of the parcel, has some frictional component to it. And then there's large generation by drag the whole time this parcel is coming north. And then, interestingly, a new rain cell forms, and it kind of pushes down the parcel very, very subtly. And at that point, you have positive tilting of the crosswise vorticity during these couple of descents. So this is seemingly environmental and drag-generated vorticity that's being utilized to create the second tornado in the model. So I guess the takeaway here is that friction for this simulation and for these parcels is dominating the generation of vorticity that becomes important for both tornadoes. This one could be a little bit more environmentally driven, and this is a more unusual tornadogenesis mode. This is this type of thing has been seen kind of like along flanking lines in new developing cells. You can get tornadoes sometimes, but this is a more unusual way of doing it. But in both cases, the baroclinic term is just tiny compared to the frictional term. The frictional term is orders of magnitude larger. Okay, so I mentioned earlier that these internal momentum surges have been observed several times. They're basically ubiquitous in supercells in both simulations and observations. So we can look at, because we'll look at the surge that was closely related to tornadogenesis for tornado 1. And so now we're going to look at, this is a basically a perturbation temperature field. So there's this initial surge that I won't talk about, goes away, it doesn't do anything. And then the tornado triggering surge shows up first around 2208, moves south. It's warmer than its surroundings, so it's relatively warm in the cold pool, which is interesting. Here's the pre-tornadic vortex. Here's the internal surge. We can look at parcels that wind up in the tornado a few minutes later, and these are the circle black dots here, and a lot of them show up in the internal surge. So that just kind of shows, okay, yeah, the internal surge is actually important for tornadogenesis. Interestingly, the internal surge has parcels that are coming both from the southeast and kind of taking this track around, and then from the northwest and coming in. So the question becomes, okay, there's these two very well-defined trajectory paths that are going into this internal surge. Which one's more important? Just briefly, in terms of the forcings along these trajectories, the ones that are along this red line, these descend from a lot higher, and this is the different forcings along the trajectory. The forcing is dominated by dynamic pressure forces for the red line, for parcels that are typical of the red line. Whereas for the yellow line, the forcing is dominated by negative buoyancy, so rain and water loading. Okay, so which one is it? And I noted earlier that the internal surge is warmer than the environment, so it would seem that the dynamically forced ones are more likely driving the internal surge, and that these ones are maybe just getting mixed in. So to verify that, I looked a little bit earlier in the simulation, and you see that here's these path 2, I'll call it, and path 1 trajectories earlier. This is 2 minutes earlier, maybe. All of the parcels were in the internal surge were on path 1. So we're going to say, okay, path 2 is just getting mixed in. It's just kind of it's an artifact of the surge being on the ground for a while and kind of mixing, whereas path 1 is the important path. So given that, the question I wanted to answer is, okay, so you have these parcels that are being dynamically forced to descend. Why is that going on? Why is that the most important thing for the internal surge? How is that creating the surge? So I looked a little bit up in the storm. This is 2.5 kilometers above ground level. The dots are parcels that wind up at the ground in the internal surge. You can see that they're all in this kind of ridge of relatively high pressure. This is a perturbation pressure plot. In between the environmental inflow into the mesocyclone and kind of, this is the environmental flow. So this is the storm relative kind of curved updraft, and then this is the environmental flow to the west of the storm. So there's this convergence that's going on between the two that's creating, I guess, this kind of, it's almost like a stagnation flow, high pressure. You can look at that in a cross section and see that most of the parcels are just below this maximum of perturbation high pressure that's in between the inflow and the environmental flow. Looked at in a different way, this is the vertical pressure gradient, perturbation pressure gradient force at 2 kilometers above ground. And so you see they're all in this negative area. So there's strong perturbation pressure is forcing these parcels down in kind of a blocking flow pattern. And just confirmed, if you take a cross section, you can see that, the parcels are all kind of just in this area, and this is going on because these two areas are meeting, and they're forcing parcels to descend. I was never able to, one question I always wanted to answer when I was doing this that I never really got to, because it was, the simulations are so complex. If this is the driving force, so if it's this blocking flow, why is it modulated into surges? Why isn't it just a continual downdraft of parcels? And I don't have a good answer for that. The only thing I could really speculate is that because the storm is undergoing so many strength change, the updraft is very not steady. It's there, but it strengthens, it weakens, it strengthens. So my guess is, and showing this was basically impossible. So we said we'll do it in the future, and then I quit. No, but if I guess potentially with these modulations in storm intensity, you may have situations where the forcing between the environmental flow and the convergence intensifies and weakens. Maybe if the updraft intensifies a couple of minutes later, you get an increase in this perturbation pressure. And maybe that's why you're getting it to be pulsed and surges rather than just a continual downdraft. So I guess just in summary to wrap this up, I hope I've shown that you can do a lot with these simulations. And the role of surface drag in tornadogenesis is very different from the generally accepted mechanisms that have been out there. Another student that was in CAPS while I was there did a very idealized study of a tornadic supercell and also found that surface drag played the most important role in the generation of vorticity in a tornado in that simulation. It's kind of a different scenario because the tornado forms very early in that simulation, so it forms before a lot of the rain does. Recently, Markowski and Bryan and Markowski have been doing a lot of work showing that the drag is probably overdone in these simulations because the eddies that should mix out some of the drag are not resolved. Paul Markowski has a very good presentation from SLS this year that gives a good summary of this issue. It's more of an issue. My understanding is it's more of an issue in the inflow, so where things are more laminar. The drag parameterization is probably way overestimating the amount of shear that's in the lower atmosphere, and in a more mixed kind of outflow area, it's probably not as much of a problem. But either way, it would have to be over an order of magnitude greater to really overcome the fact that drag is dominating the forcings along these trajectories to completely invalidate this. But when I spoke to Paul at SLS, and he said he's trying to solve this problem, and it's mainly just banging his head against the wall trying to solve it. But he has some ideas, so I look forward to seeing what come out of that. I think that's pretty much all I have at this point. So I'll take questions.
Okay, questions for Alex?
Yeah. So it seems to me that in all these processes, there's nothing that kind of differentiates the direction of rotation. So is that any sort of dynamic reason to favor
Cyclonic.
clockwise or
Yeah.
counterclockwise rotation?
I think it's the shape of, so you have this overall, the storm overall has a cyclonic mesocyclone, and that kind of sets the stage. Everything kind of has that kind of sense of rotation. But you could get, I mean, there are I don't plot it, but there's plenty of anticyclonic vorticity. It just doesn't persist because it doesn't get favored. It's not favored to go in under the updraft and stay under the updraft. There's a lot of symmetry, so like on the south side of a surge, you would have anticyclonic vorticity, but that part of it will go south and not into the updraft. And the north part, where you have the cyclonic vorticity, is going to get wrapped into the updraft, and you really need that updraft to stretch the vorticity. The big thing is, if you have a source of vertical vorticity under this updraft, it's going to stretch and it's going to make a strong vortex because the updraft's so strong. So any source, I mean, if you take drag away, I did a simulation. You take the very beginning of this simulation, you turn off surface drag, you just run the model. Some weird stuff happens because you're all of a sudden really messing with the environment. Everything accelerates, but you actually do. You get a very, very short-lived but very intense tornado without surface drag because the updraft is there. So all of a sudden, the baroclinic term becomes the most important term. Because there is a baroclinic term, it's just small, but everything is exponential. So I think just given that scenario, given a strong updraft, it really depends. And this is kind of the thing about that I like to complain about people not using surface drag in their simulations of these types of storms. If you take it away, then the next term is going to dominate because it's such a runaway process. Any important vorticity, or any vorticity that's the most important, is going to get stretched and turned into a tornado. But I think that overall sense is just, it's in the northern hemisphere you have the cyclonic supercells are favored. That's the wind shear that's set up.
Other questions? Hank?
Yes, I have two general questions. In the very beginning, you mentioned two favorable conditions. One is the wind shear, another is the instability.
Yeah.
I did not seem to see much discussion of the wind shear. When you share the favorable condition, what is that? Is that environmental?
Yeah, environmental. Turning with height, yeah.
Is the low wind shear is more favorable?
No, high, like strong wind shear, turning with height, low level, strong wind shear, turning with height.
Okay, in terms of instability, I'm thinking, since we also see tornado in winter seasons, or different from the spring instability. So when you're talking about instability, in addition to the baroclinic instability, is there any other instability work as well?
So I think that sort of roll-up instability type of thing maybe is, I think in general, papers that have looked for that have had a hard time finding. You would expect a symmetry in that you see like 4 of those types of things, right? You see a tornado and then an amount of spacing and then like a constant, and it should be really well predicted by the theory. In general, those aren't observed. You do see that like water spouts. There's like really famous pictures of like 8 water spouts in a row. And in that case, that's a shearing instability that's just getting released under an updraft. And it's very periodic. But I think for the wintertime, things are dominated by the outflows, and the shearing instability is kind of a second order effect. You probably see that once the tornado develops, you'll see like subvortices. That's a barotropic instability that gets released, the satellite vortices.
Brian?
So I'm just curious about these vortices. It's like the one you showed.
Yeah.
I'm just wondering, I'm just curious why there's just one of them, or maybe it just seems like it's just odd that there's like one vortex, given that there's all these trajectories swinging around.
Yeah.
This frictional vorticity.
Right. Yeah. Why not like a line or yeah. I think that it has to do with the updrafts, the updraft shape. So let's see if I can find a good example. Okay, so this one, the contour, the light shading in the background on this is vertical velocity. So there's this enhanced kind of circle, I guess, like circle of enhanced vertical velocity. So right on the edge of that, you have very enhanced tilting of vorticity, whereas the flow is coming in and encountering it in a way such that it makes a favorable place for just kind of a continuous flow of parcels. And I also think that's why this one's anchored to the updraft. This one doesn't move much. If you remember in those slides I showed, the V2 just kind of stays put. I think it's because the parcels are just coming in and flowing into the same place that's favorable to tilt the vorticity. And then along here, you will see vortex sheets. So if I lower the contour threshold a lot, you'd start to see like sheets of vorticity, kind of like you're mentioning. But I think it's just there's a lot of asymmetry that breaks this up and favors areas to.
And just a quick follow-up. I mean, there's always friction.
Yeah.
In the real world.
Right.
And then you mentioned these bursts that happen all the time. So
Yeah. Why don't we have
see more
tornadoes constantly? Yeah.
You know,
Yeah.
There's a lot of false alarms.
Yeah. No, I think you still need that thermodynamic stuff that I showed earlier with kind of the temperature. I think that's very important in getting the background set up. I think if you have too much cold outflow, you can't align things like they need to be aligned. So I think that the importance of cold outflow is more cold outflow, but not too much cold outflow and just enough cold outflow is more to get everything aligned. And I think some of the stuff has shown that, like some of the toy simulations that Markowski has published have shown that too. It's basically the importance is the alignment. So even if the vorticity is being generated by friction, if all the air parcels are just rushing away from the updraft because there's too much cold air, you can't get a tornado. And so you need this kind of right microphysical situation and correct drop size. I mean, it gets down to drop size distributions, like how cold that cold pool gets and how moist the atmosphere is at really fine levels. So I think that's the main thing. I think that there is a Goldilocks situation here, but it's not a Goldilocks situation to create vorticity. It's a Goldilocks situation to create the right alignment in the updraft with the low-level features. So that's my 2 cents on that. Yeah.
From an oceanographic point of view, special variations of bottom drag report for generating Thunderstogenesis on, say, continental shelves, and what will work maybe 100 meters, 200 meters deep, and then sharp drop-offs
Mhm.
and topographic features. So it's not something that you have to deal with, but it's still very important bottom drag.
That's interesting. Yeah, I mean, I know that there's the effect of kind of topographical. There's been some interesting stuff. I think Llewellyn has looked at that, like for LES simulations for vortices, and you see weird behavior when you put like a hill or a drop. But yeah, it gets pretty hard to keep track of. Yeah.
I have a question.
Yeah.
So you hinted at this at the end, but when you published this paper, it kind of set off a mini firestorm in the community, right?
Yeah.
For years, people didn't use friction on their simulation.
Right.
So have you noticed, I know you have a different job now, but have you noticed in severe storms modeling work that you've essentially kept people honest, and that there's more studies that are turning surface drag on?
Yeah, it at least gets mentioned. So it used to be that you'd set up a simulation and it would be like, and we used a free slip because that's what they did in the 80s, and you know, we get this amazing tornado, and so clearly we have the whole story is over. Now it's like we didn't use drag because, and then they'll say, yeah, it's like a justification as to why not using it. The other thing is, as the data assimilation stuff comes along, you cannot assimilate low-level observations into a model without surface drag turned on. It's a dynamical inconsistency, and it makes no sense. And anyone that's tried that, I've seen conference papers many times where people have not had surface drag on in their simulations, and they're trying to assimilate like sticknet data or something really, and it doesn't work. And then they don't publish it because it just doesn't work. You can't. There's not a consistent lower boundary condition, and the thing that's making the wind shear, you don't even have in your model. So how do you think your model is going to fit that space? It just can't be done. So I think that as we do more data assimilation, you should see like if studies based on data assimilation have to use surface drag. So maybe we can get this figured out.
So that the question is, what kind of observations can you use? Can you imagine any observation that
Yeah,
you
it's-
use to sort of differentiate?
It's really tough.
So,
You need, yeah, I mean, you
what
would.
can Michael do?
Yeah, I know, right? Yeah.
What
No,
can you do?
yeah, I mean, really, really high temporal frequency, right? So, I mean, I think you've done some of that, right? really, really high temporal frequency with really high spatial resolution. That's cheap, right? That's the problem. It's easy to do.
And really close to the ground.
And really close to the ground. Yeah, it's tough. I don't know, like LiDAR stuff, maybe you could, but I don't know, that didn't work very well. So the thermodynamic stuff is interesting. I mean, I know that people are basically on this one thing, kind of in answer to your question earlier, people are still on the hunt for baroclinic vorticity generation because they think it should be there. So they're looking like all over the storm now. So like people are shooting rockets into storms to look to see if maybe the temperature gradient is aloft and that's where the rotation's coming from. But yeah, the upper level stuff, nobody knows what's going on even 500 meters above the ground. I think there's an interesting, when I was working on the case previous to this, there's an instrumented tower west of Oklahoma City that has since long gone out of commission because there's no funding for it. But I believe in the 70s, a supercell passed pretty close to it. And the inflow, the vorticity from drag in the inflow is unbelievable. There's really, really strong low-level shear. Like I think it's 400 meters tall, and there's just amazing low-level shear. And I mean, they're explaining that you have to have drag for that. So I think instrumented towers would be interesting, but you have to get lucky. I mean, you put up a 400-meter tower, and you have to get lucky that a supercell passes within 10 kilometers of it. That's an expensive gamble. It's easier to drive to it, I think, but then it has to be remote. So I don't know.
All right, we can continue the discussion at lunch, which is going to happen now, and then for the graduate students, Alex would love to talk to you about research or taking a different career path. And more important, he'd love to talk to you. So we'll see you at lunch, and let's thank Alex again.